Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 2, Lesson 6 on isosceles triangles. Now, this entire unit is really about transformations and seeing what we can learn about geometric objects through transformations. Last lesson we did line reflections and there was a very important problem on the homework, the last problem pretty much, that I hope that you went through. We're going to kind of review that in our first exercise today. But let's jump right into it and see what we can learn about this very important idea of isosceles triangles through the use of transformations. All right, isosceles triangles. As you've probably learned in the past, an isosceles triangle is any triangle with two sides of equal length. Some people would even consider an equilateral triangle, which has three sides of equal length, a sort of subcategory of the isosceles triangle. Now, they have very important properties that we can explore and explain specifically through the use of transformations. So let's get into it right away in exercise number 1. In the diagram shown below, triangle ABC is isosceles with segment AB congruent to segment CB, shown with dashes. Ray BD is the angle bisector of angle ABC, known as the vertex angle of the isosceles triangle. Letter A. What two angles must be congruent based on Ray BD bisecting angle ABC? State them below and verify using tracing paper. Okay, great. Why don't you go ahead and do that? All right, now keep in mind, right, earlier on in this course, we talked about the fact that every angle, forget about isosceles triangles, every angle has a unique angle bisector. And all we're saying in this problem is that for angle ABC, right, BD is that unique angle bisector, which of course means that this particular angle is congruent to this particular angle, and those two angles happen to be angle ABD and angle CBD. All right, angle ABD and angle CBD. All right, let's take a look at letter B. Based on properties of rigid motions, explain why triangle BCD would map on top of triangle BAD if reflected across ray BD. Use tracing paper to verify this mapping. Okay, so my claim is, using what we've already learned about line reflections and specifically what we learned in the previous homework, if I reflect triangle BCD, here outlined in blue, across ray BD, it will map on top of triangle BAD, triangle BAD. All right, so why is that? Well, first, what we should know right away, right, is note where each one of the three vertices gets mapped to underneath that reflection. Well, notice, points B and D lie on the line of reflection, so when we reflect those 2 points in that line of reflection or that ray of reflection or whatever, they're not going anywhere. So first, let's go with that. Points B and D get mapped to themselves because they lie on the line of reflection. Now, the only question now becomes, why would point C have to get mapped to point A? And that's what we explored in that homework problem, okay? And this is very important, right? Point C will get mapped to point A because two conditions are true. The first one being that these two angles are equal. And remember, reflections preserve angle measure. So even if this wasn't an isosceles triangle, because those two angles are congruent to each other, when I reflect this triangle across that angle bisector, the image of point C would have to lie somewhere along ray BA in order to keep the two angles the same. If it got like somewhere out here, well, then the two angles wouldn't be the same anymore and a reflection wouldn't preserve angle measure. But not only does it land on ray BA, it must land exactly at point A because it is the same distance away from B as A is, right? So because reflections also preserve distances, it must land on A. It's got to land somewhere on ray BA because reflections preserve angle measurements. But then it must land exactly on point A because reflections also preserve distance. Now I'm going to summarize all of that by saying point C maps to point A because, that doesn't look like because, angle CBD is congruent to angle ABD and this is critical, and because BC is congruent to AD. All right. If either one of those two things weren't true, point C wouldn't get mapped onto point A. All right. Or at least we wouldn't know that it would have to. Now, finally, right, what does this tell you about, and actually, let me do the reflection. Sorry, it says, you know, use tracing paper to verify, right? If I actually take this triangle and I reflect it, which in this program is flipping it left-right, then I see that it immediately flips over and lands on triangle BAD. Now the fact, right, that when I reflect that triangle across that ray, it maps exactly onto this triangle, right? What does that then tell you about those two triangles? Well, this is critical. It tells you the two triangles are congruent, right? They are congruent, right? They're identical triangles, all right? They have the same size, they have the same shape, they have the same length of sides, they have the same angle measurements, all of that. Okay, and that's absolutely critical because then we can do problem D. Given C, in other words, given the fact that those two triangles are congruent, write down segments or angles that must be congruent to the ones given. All right? So again, keep in mind, right, what we're saying here is that this triangle, and let me do it in a different color, and this triangle, of course it's going to kind of overlap there, those two triangles are identical. They're congruent. Okay? So that means that AD, which is right here, must be congruent to CD, which is right here. They have to because they are what are called corresponding parts or corresponding sides of two congruent triangles. AD must be congruent to CD. Okay? See if you can fill in the rest of that. And actually, let me make some marks, right? To show AD is congruent to CD, I'm going to make a double slash mark there. Angle A, which is right here, has to be congruent to angle C because those are corresponding angles in two identical triangles. So angle A must be congruent to angle C. Let me mark those with arcs. All right. And finally, angle ADB, right, which is this one right in here, must be congruent to angle CDB. And maybe I'll put a double arc mark there. Arc mark. Sounds like an aardvark, except not quite. All right. Let's take a look at letter E. Explain why angle ADB and angle CDB must both be right angles. Base your explanation on facts that you know, not just how the angles look. Now remember, what do we know about angle ADB, which is right here, and in the previous one I marked it with two arcs, and angle CDB. One thing I know is that they're congruent to each other, right? And they're congruent to each other again because I know that this triangle is identical to that triangle. But why do they have to both be right angles? Pause the video now and see if you can write something down. Well, there's a bunch of different ways to say it, right? But the plain fact is angle ADC is a straight angle, right? Angle ADC is a straight angle, which means angle ADB and angle CDB have to be a linear pair, right? So because angle ADC is a straight angle, that means angle ADB and angle CDB are a linear pair. And of course, what do we know about linear pairs? It means they are supplementary. All right. Well, what does it mean for two angles to be supplementary? It means they have to add up to 180 degrees, right? Linear pairs add up to 180 degrees. Now, normally, you could have, all right, maybe this one's 80 and this is 100, or this one is 120 and this one's 60. But these two angles are congruent to each other, and since they're congruent to each other, they both must be equal to 90 degrees. Since they are congruent angles, they must each measure 90 degrees. End of story, right? So now, one final piece, letter F. Give one term that would describe the relationship between ray BD and base AC. All right, let's mark some things we know, right? We know these two triangles are congruent, all right? We know that that means that AD is congruent to CD, and we know that those are both right angles. So what is one excellent term to describe the relationship between BD and AC? Pause the video now and see if you can write something down. Well, BD is perpendicular to AC, and BD bisects AC, so ray BD is the perpendicular bisector of AC. It's cool, right? So if I draw in the angle bisector of an isosceles triangle, it becomes the perpendicular bisector of the opposite side of what's known as the base of an isosceles triangle. All right, let's take a look at a lot. Like that was a lot. That was a lot. Let's look at important properties of isosceles triangles that we just figured out in exercise 1. That's right, that was all exercise 1. Let's take a look. Number 1, the base angles of an isosceles triangle are congruent. They have equal measures. Another way to state this is that angles opposite congruent sides are congruent. Number 2, the bisector of the vertex angle in an isosceles triangle is also the perpendicular bisector of the base of the isosceles triangle, i.e. the side opposite of the vertex angle. All right, so again, probably number 1 is more important than number 2, but both of these get used a lot. And I just want to really quickly backtrack just for a moment to really make sure that we understand this, right? This idea that if we've got an isosceles triangle, right, the angles that are opposite the congruent sides also have to be congruent. Okay, absolutely key. So if you've got a triangle that's isosceles, two sides are congruent, then the angles that are opposite those two congruent sides are also equal in measure, are also congruent. Again, less important, the fact that when we draw in the angle bisector of the vertex angle, so in every isosceles triangle you have two what are known as base angles, and then the third angle is known as the vertex angle. That vertex angle, when we bisect it, that bisector will be the perpendicular bisector of the base of the isosceles triangle. Really, effectively, cutting it in half, and those two halves are each congruent right triangles. Congruent right triangles. Okay. Now, before we move on, let's recall a fact that you learned in middle school and you've been using for a while, and we will eventually prove in this course. The sum of the three angle measures of any triangle is equal to 180 degrees. It's a remarkable property in geometry, and again, we will prove that when we look at parallel lines and a bunch of other things later on. But for right now, we're going to take it as a fact, because it is, and we're going to use it to find some missing angles. All right, let's take a look at exercise number 2. In triangle LMN below, segment ML is congruent to segment MN, and the measure of angle LMN is 114 degrees. P lies on LN such that segment MP bisects angle LMN. Letter A. Mark the two congruent sides of triangle LMN. All right, great. Go ahead and do that. It should be obvious from what they told us. Also kind of obvious from the picture, but we should definitely just use what they told us. Pause the video and go ahead and mark those congruent sides. All right, we're going to be marking a lot of congruent sides and pictures in the future. So just again, this idea that we know that ML, which is right here, is congruent to MN, and we do those with little slash marks. All right, that's very simple. All right, letter B. Mark the two congruent base angles of triangle LMN. All right, so again, it's kind of key here, although it looks like there's two triangles here, and there definitely are. You could, the big picture here is that we've got an isosceles triangle LMN. And what we know is that sides that are opposite, or angles that are opposite, congruent sides will be congruent. So those two angles must have the same measure. All right, let's take a look at letter C. Using the angle sum fact above to use the angle sum fact above to determine the measures of the base angles of triangle LMN. Mark these on the diagram. Okay, so let me just draw this diagram, but without that angle bisector thrown in. So we've got LMN. We know that this thing is 114 degrees, and we know that those two angles are equal, right? So the easiest thing to do is to take 180 and subtract 114. All right, that's why I've got my handy calculator. 180 minus, 180 minus 114. Of course, you can be doing this with your graphing calculator as well. So that's 66 degrees. That is, if you will, what I have left over to split up amongst these two angles. Since those two angles are equal, each one of them must be 66 degrees divided by 2, or 33 degrees, right? So each of those base angles has to be 33 degrees in order for the three angles of triangle LMN to add up to 180. All right, let's look at letter D. What is the measure of angle LMP? Mark this on the diagram. All right, fantastic. Well, LMP, right, LMP is this angle right here. And we can figure that out easily because we know, or we're told, that MP bisects angle LMN, right? So angle LMP, measure of angle LMP, must be 1/2 of 114 degrees, right? Easy enough, right? 114 divided by 2, and that's going to be 57 degrees. And they ask us to mark that on the diagram, so I do that. And finally, letter E. Use the angle sum fact above to verify that angle MPL must be a right angle. All right, again, simple enough, right? We know that within triangle LMP, just triangle LMP, that those three angles must add to 180. And we have two of them, the 33 degrees and the 57 degrees. So it's easy enough to just take 33 degrees, add 57 degrees, and get 90 degrees. And then we can say the measure of angle MPL must be 180 minus 90, or 90 degrees, right? Got to be 90. In order for those three angles, right, 1, 2, 3 to sum up to 180, that's got to be 90. And again, that just verifies what we already knew, which is the angle bisector of the vertex angle must be perpendicular to the base. Okay, awesome. That extra one was there just for this work. We didn't need it. That's okay. Now, it is not unusual at all, right, for an isosceles triangle to show up in a problem. It will be important to be able to determine both vertex angles and base angles when we see these types of triangles, because they're going to come up a lot in this course, okay? So let's take a look at exercise number 6, where we just do some numerical work. It should be pretty easy. For each isosceles triangle shown below, find the missing two angle measures. All right, so let's take a look at triangle ABC. In triangle ABC, the only angle we know is this 66-degree angle, but we know that side length AB and side length CB are the same, which means that this angle and this angle have to be congruent. And that immediately tells us that the measure of angle C must also be 66 degrees. All right, so that's one of the two missing angles. Now, the final angle, which is the vertex angle in this case, we can now figure out by simply doing 66 degrees plus 66 degrees and getting 132 degrees, right? No, wait, no, 6, 6, 12, 122 degrees. $132, I was right to begin with. Yeah, geez, man. 132 degrees. And now I can subtract that off from 180. This is why I should never try to do addition or multiplication just in my head. Then I just do 180 minus 132, well, unless the numbers are small. And I'll get the measure of angle B, which is 48 degrees. I'm going to just throw that in there. All right, simple enough. So it's kind of cool. If we're given an isosceles triangle, and we know the two sides that are congruent, and we're given even a single angle, we should be able to figure out the measure of the other angles. Now, in this particular case, we knew one of the base angles, so immediately we knew the other base angle. We could just add those two together, subtract their sum from 180 to get the measure of the vertex angle. Let's take a look at letter B. All right, in letter B, we've got triangle EFG with segment EG and segment FG congruent, and we know that angle G is 90 degrees. Okay, well, here's the key. This time what we're missing is we're actually missing the two congruent angles. Now, this is a very special case. This is what's known as an isosceles right triangle. And we'll see isosceles right triangles fairly frequently in this course. But it doesn't really matter that it's an isosceles right triangle. What matters here is that we know the measure of the vertex angle. We know that that's 90, right? So we know that what we've got left is another 90 degrees, right? If we have 180 and we subtract our vertex angle, we get 90 degrees. And that means that measure of angle E, which equals the measure of angle F, must be 90 divided by 2. And that means each one of those has to be 45 degrees. All right, in an isosceles right triangle, right, a right triangle, right? It has a right angle and then two legs that are congruent. The two acute angles have to both measure 45 degrees. All right, what I'd like you to do is do letter C all on your own. All right, now you always have to watch out the orientation of the triangle. It could be in any different way, sitting in however way they decide. It's critical here when you look at this triangle to realize that that 50 degrees that you're given is not a base angle. It's actually the vertex angle. And again, all you have to do is sort of draw these arrows from the two congruent sides to the opposite angle, and you will see the two congruent angles. So in this case, to figure out those two angle measures, and they're going to be the same, all we have to do is do 180 minus 50, which gives me 130 degrees. That 130 degrees now needs to get split into, right? And each one of those things will be equal to 65 degrees. That one I think I can do in my head. I don't know why the 66 plus 66 was throwing me off. I just kept looking at it and going, I don't know, that seems like 112. Anyway, it wasn't. So, easy enough. And we have to be prepared to do this, where we're given one angle in an isosceles triangle and use two facts. One fact being that the base angles, or angles across from congruent sides, are congruent. And then the other fact that the sum of the three angles must be 180 to fill in all other angles. All right. Let's take a look at one more problem. Exercise number 4. The ratio of the measure of either base angle to the measure of the vertex angle in an isosceles triangle is 3:2. Determine the measure of the vertex angle of this isosceles triangle. All right, we got this ratio thing going on again. Let's first draw out kind of a generic isosceles triangle. All right, and let's mark these two as being the congruent sides, because that's what it looks like. Now, it says the ratio of the measure of the base angle to the vertex angle. So in this ratio, 3:2, this is the base and this is the vertex. Now, that means that what I should do is I should label each base angle 3 times x and my vertex angle as 2 times x. Right? We saw this little trick come up before. It's going to come up a lot in this course where we're given ratios like 3:2, 5:3, whatever. And then we would just randomly attach an x to keep that ratio consistent. Once I have this, it's really quite easy, right? All I have to do is do 3x plus 3x plus 2x is 180, right? That's 8x is equal to 180. And x is 180 divided by 8. Let me do that really quick here. 180 divided by 8. So x will be 22.5. All right. And finally, I want to know the measure of the vertex angle. The vertex angle is 2x. So my vertex angle must be equal to 2 times 22.5, which is going to be 45 degrees. All right, that's it. Let's do a summary. Now, what we saw today was a lot about isosceles triangles. And we primarily learned about them through the idea of reflecting half of the isosceles triangle over the angle bisector of the vertex angle onto the other half. And what this showed us was a lot of things that we probably already kind of knew about isosceles triangles. The idea that there must be two equal angles because there's two equal sides. The idea that if we draw that angle bisector in from the vertex angle, it ends up being perpendicular to the other side, kind of dividing every isosceles triangle into two identical right triangles. But the big takeaway from today, the one that we will see come up a lot in this particular course, is the idea that angles that are opposite congruent sides in a triangle are themselves congruent. They have the same measure. All right. Again, we'll see that a lot in future lessons. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.